We dream of bottling the power of the stars, a clean, nearly limitless source of energy born from the heart of our sun. But recreating this stellar fire on Earth is one of humanity's hardest challenges. Here's why nuclear fusion is so hard, yet so worth pursuing. Why nuclear fusion is so hard on Earth. A visual journey into star power, engineered for Earth. Let's start with what fusion really is. Fusion is when light nuclei, like hydrogen, join to form heavier nuclei. They repel each other electrically, so getting them close is tough. If they touch, they fuse, releasing tremendous energy. A tiny bit of mass converts to energy. That's the fusion payoff. On Earth, we often aim to fuse deuterium and tritium to make helium and a neutron. In the Sun's core, fusion runs naturally. Immense gravity squeezes particles together, overcoming their repulsion. Energy created at the core eventually escapes as sunlight. That's star power. Stable, constant, self-sustaining in a stellar furnace. But Earth is not a star. We lack the Sun's sheer mass and crushing gravity, so we must fake star-like conditions with machines. Gravity bends space-time, funneling particles toward the core. That compression raises density and pressure enormously. High density increases collisions, key for fusion. On Earth, we must replace gravity with heat and clever confinement. To collide, nuclei need incredible speed, meaning heat. We're talking tens to hundreds of millions of degrees Celsius. At these temperatures, matter becomes plasma. For some fuels, even hotter than the Sun's core is needed on average. Plasma is a soup of charged particles, electrons, and ions. Because it's charged, it dances to the tune of magnetic and electric fields. But it's unstable. Waves and turbulence can tear confinement apart. We must hit the triple product: temperature, density, and confinement time. Plasma destroys ordinary containers on contact. It cools instantly, damages walls, and contaminates the plasma. Even tiny touches trigger instabilities that bleed energy away. So we suspend plasma, held up by magnetic fields or inertia. Enter the tokamak, a torus-shaped magnetic bottle for plasma. Powerful coils generate fields that wrap the plasma like a donut. Key parts: toroidal and poloidal fields, vacuum and exhaust systems. Together, they aim to confine superhot fuel long enough to fuse. Magnetic fields bend charged particles into spiral paths. Tokamaks combine toroidal and poloidal fields for stability. Ideally, particles stay on nested magnetic surfaces, away from walls. When it works, confinement is beautiful and fragile. Edge instabilities can push plasma into the wall. Turbulence degrades confinement, cooling the plasma. Disruptions can abruptly end the pulse and stress the machine. Active control and clever design fight these effects. Plasma behaves like a living fluid, full of waves and modes. Kink modes, ballooning modes, and edge-localized modes can erupt. We use sensors and feedback coils to tame the chaos in real time. Stability is possible, but always on the edge. Next hurdle: getting more energy out than we put in. Heating, magnets, and support systems demand serious power. As fusion improves, the balance tips, but slowly. We chase a high Q factor, net energy gain. Deuterium-tritium fusion prefers around 100 million degrees. Heating methods include radio frequency waves and neutral beams. At temperature, collisions become frequent enough to fuse. Reaching it is hard. Holding it is harder. Another path is inertial confinement. Compress with lasers. A perfect squeeze must be fast, even, and extreme. Done right, the core briefly ignites, like a tiny star for a moment. It's a heartbeat of fusion, measured in nanoseconds. But imperfections spoil symmetry and waste energy. Shocks must align perfectly, or the hotspot never forms. Even with ignition, overall system gain remains a challenge. Target quality and laser efficiency are critical bottlenecks. Real reactors are feats of engineering on every level. Materials must survive heat, radiation, and magnetic forces. Precision assembly and remote maintenance are essential. Fuel breeding, heat extraction, and safety all interlock. Around the world, teams push the frontier. Together, records improve, hotter plasmas, longer pulses, better control. Alternative designs offer stability and efficiency trade-offs. Smarter control and stronger magnets could tip the balance. Imagine a compact star in a jar, powering cities. No carbon, abundant fuel from seawater, and minimal long-lived waste. The journey is long, but progress is real and accelerating. With patience and innovation, we can harness starfire safely. From the sun's heart to our blue world, we strive to turn a cosmic phenomenon into human progress. Science is a relay, each breakthrough a baton passed forward. And fusion may be our brightest relay yet. Fusion may be the hardest challenge on Earth, but it could be our brightest future. If you enjoyed this, like, share, and subscribe for more science stories. Thanks for watching.